Okay, guys, so just checking the calendar to make sure I wasn't misremembering. You guys have the little test 1 coming up on this next Monday. You guys have the little test 1. I figured I would just say a few words about that before we started the lecture today. So I haven't actually written the little test yet. I will do that probably the next couple of days. But it's going to be about 30 questions, true or false, multiple choice. And it's going to be comprehensive, covering what we learned from, let's say, the very first unit up through today. And the questions aren't supposed to be challenging or tricky questions. They're not supposed to be anything like homework questions. They're supposed to be just like quiz questions. So if you guys have been taking the quizzes and doing, let's say more or less well in the quizzes, then you should not be expecting much different here. So 2 good ways to review. One is just to go back through, if you go back through all of the lectures that we've had so far, if you look at the start of each lecture, I summarize the previous lecture, right? What we did last time. That gives you like the high level points as to what you're supposed to know about a method or about a topic. Those are definitely good things to review. So just, if you don't want to look through all the slides again, which obviously would not be a bad idea, you can just look at the recaps, which kind of try to hit the main points. And in addition to that, I would go back through the quizzes to make sure you understand the answers to the questions that we asked, if not post-Piazza questions. You can also go to previous versions of the course. If you go to the course website and you type in -F16 at the end, capital F16, that's the last time I taught this course, fall 2016. You can actually, I believe, just take the quiz, or like at least look at the quiz questions for all of these topics. There's just going to be more questions kind of the same flavor that you would be seeing on the little test. And if you go to, I don't know, in the time I taught it before that, maybe F15, let's try that. Yeah, there's fall 2015. If you go to the teaching page on my homepage, it'll link all of these. Let's see, maybe I taught it in spring 2015 as well. So there are lots of quiz questions here. It's like a repo of good practice questions. Okay, any questions about the little test? Yes? I think that the quizzes are all in practice mode, which means you can just take them. They tell you immediately whether it's true or false, right? So that gives you the answer. Every time you take the quiz, you just get the answer back for that question. Yeah, so we can change that. So Kartik and Biswal, we need to just put the quiz in practice mode. Allows people to retake questions. So we'll change all the quizzes to be in practice mode. We can do that as soon as we'll do it very soon. I didn't mention one other thing. Maybe you have a question though. Yeah. Yes, I was going to mention. I don't like the word cheat sheet. I think it's kind of an unfortunate, name. But let's say note sheet. You're allowed a front and back page of notes. You can make it as small font as you want. You can bring a microscope, or you can just write it by hand. So yeah, you're allowed a page of notes front and back to bring with you. Any other questions? Okay. So that'll take place of lecture on Monday. So we'll have that instead of lecture, and then after that we'll jump into the second order methods unit. Let's talk about the last lecture we have on duality. At least in this unit. Later in the course we'll talk about dual methods. It's a kind of a broad, a term that I'm using to refer to a broad class of methods that includes things like ADMM, which you may have heard of. It's a very popular method these days. So we'll revisit duality later. We'll actually also revisit duality when we talk about interior point methods. So you'll see it pop up various other points in the course, but this is our last kind of lecture on duality theory, let's say at least. So last time we talked about the KKT conditions. They stand for Karush-Kunducker conditions, and we actually proved that they are necessary and sufficient under strong duality. Okay? In fact, they were necessary under strong duality, and they are always sufficient for optimality. So we have a general form problem, minimize f subject to hi of x less than or equal to 0 and lj of x equal to 0 for a bunch of inequality and inequality constraint functions. And the KKT conditions are a set of 4 conditions on a primal variable x that corresponds to this optimization problem and a dual pair uv that corresponds to the dual of this optimization problem. Okay? The first one says that x minimizes the Lagrangian at the point uv. So if you look at the Lagrangian fixing the dual arguments at u and v, if you look at the Lagrangian over all x, the x that you have minimizes the Lagrangian. So said differently, if I take the Lagrangian, which is just the criterion plus, these terms, sum of ui hi plus sum of vj lj, then thought of as a function of x for u and v fixed, if I take a subgradient of this, it contains 0, which means that it's minimized at the x I'm looking at. That's called stationarity. The second condition was called complementary slackness. It says that either the ith dual variable ui or the ith constraint hi of x has to be equal to 0 at the solution. So ui is constrained to be bigger than or equal to 0, and hi is constrained to be less than or equal to 0. And complementary slackness says that their product has to be equal to 0 for all I. And then the last 2 conditions are just feasibility, primal and dual feasibility conditions. Okay, so obviously if we're talking about solutions, they have to satisfy the constraints. They have to be feasible. So we actually proved that whenever these are met, okay, this implies that there's 0 duality gap. That was a very simple 3-line proof that we gave, which then implies that x is primal optimal and u and v are dual optimal. Okay, so that was the one direction. We also proved that if we had a pair of primal and dual solutions and we had strong duality, then these must hold. Okay, so we can think about them as, let's say, for a convex problem where that's strictly feasible, we know that strong duality holds. That's Slater's condition, and therefore the KKT conditions are necessary and sufficient for optimality. So they completely describe all solutions. So 2 uses of duality. We talked about the first one. We talked about the second one only in the context of a few examples, but I'll mention it in generality. So one use of duality is algorithmic. Okay, if we have any feasible x, primal feasible x and dual feasible u and v, if we look at the difference in the primal criterion at x and the dual criterion at u and v, this is called the duality gap, okay, between, let's say, x and uv. And because we've constructed the dual in such a way that, let's say, any dual feasible u and v give us a lower bound on the dual criterion, on the primal criterion, right? We've constructed the dual so that this is true for all dual feasible u and v. So that means that if I take this equation, okay, and let's say I multiply both sides by -1 and I add f of x, I get this. Okay, this tells me that the primal suboptimality, okay, between x and the very best I can make the primal criterion f star is upper bounded by the duality gap. So if I'm running an algorithm on both the primal and the dual, and it's keeping track of its iterates, and its iterates are feasible at all iterations, I can just look at the observed difference between the primal criterion and the dual criterion, and I know that that upper bounds the suboptimality in terms of the primal criterion from this relationship. Okay, it's very simple, but it's our, I guess at this point, the only rigorous way we know to stop an algorithm with a guaranteed suboptimality bound is by upper bounding the duality gap. And similarly, if I look at, let's say, G star minus GUV, So remember, the dual problem is a maximization problem. So if I look at the suboptimality in the dual, this is also upper bounded by the duality gap. Okay, so we know that how far we are away from optimality in either the primal or the dual is upper bounded by this duality gap. And this is something that we will see pop up in interior point methods, where we're going to keep track of such a quantity. So that's a very important algorithmic use of duality. Here's another important use of duality. It's less algorithmic, but it's also very practical. Given an optimal dual solution, so let's suppose we were able to form the dual and solve the dual, okay, and we had a dual solution U star V star. This stationarity condition here tells us that a primal solution, right, in fact any primal solution, must be given by minimizing the Lagrangian over all x once I plug in U star and V star, right? This characterizes primal solutions. So oftentimes that step is actually kind of quite tractable. It's easy to write down the Lagrangian and characterize a primal solution in terms of dual solutions. So that gives us kind of a, let's say, determining equation for what the primal solution should look like once I know the dual. So oftentimes that gives rise to like a unique characterization for the primal. We'll see examples for that. And that means that we can compute primal solutions from dual solutions. It's also very practical use of duality, as I mentioned, because sometimes the dual is easier to solve than the primal. So we might want to derive the dual, solve the dual, and then just infer the primal solution from the stationarity condition. We never would have to touch the primal problem at all. We only had to have written down its dual. So let's talk a bit more about that, solving the primal via the dual. So this is just repeating what I said. Stationarity tells us that once we have, let's say, a dual solution U star V star, any primal solution X star must solve this problem, right? Minimize over all x f of x plus sum of U star hi of x plus the sum of V star Lj of x. This should say Vj, which is a typo there. And because this problem is unconstrained, okay, we can often express its solutions explicitly. This is the same reason why it's often tractable to compute the dual in the first place, okay, because the Lagrangian is defined without constraints over all primal x. So it's often tractable or easy to calculate the minimizers of this. And if the minimizer was unique, then we know it must be the primal solution. Okay, we don't know that any solution of this, okay, must be a primal solution, right? Because the solutions must also satisfy complementary slackness to be primal solutions. So just looking at the stationarity condition alone is not necessarily going to give us the primal solution if there are multiple solutions to this problem. But if there's just one solution to this problem, okay, then it must be the primal solution. Does that make sense to everybody? Okay, if there's just one solution to this problem, then in order to satisfy stationarity, we would have had to have just that one x star. Okay, and even when the solution is not unique, it often gives us just an expression for what the primal solution looks like in terms of the dual, which can be very helpful. So here's a simple example of that. And I'm going to be using something called conjugate functions, which we'll learn in detail in just a few minutes. But for now, I'll just be kind of telling you that, you know, a certain thing is a conjugate, and then we'll define it and study it in a little bit. So here's an example that I took from the Boyd and Vandenberg book. Let's suppose I had a problem that it looks like it should be somewhat simple in the primal, except we have an equality constraint that kind of complicates the nature of this problem. And this is actually kind of a simplified version of a more general class of problems that we're going to be able to solve by going to the dual that we call dual decomposition problems. We'll talk about those, like I said, later in the course when we talk about methods like ADMM. Okay, but for now, let's just suppose I have a primal variable x, and I have a block representation for x. So I split it up into blocks xi. These could even just be univariate, right? Xi can just be one component of x. And the primal criterion can be written as the sum of fi of xi. So it nicely decomposes across blocks or even coordinates in the primal, except we have this equality constraint that ties all of the blocks together. Without this, right, this would be simple. I would minimize fi of xi directly for each I. With this, I can't do that. Okay, fortunately, in the dual, we're going to see that somehow the problem simplifies a lot. So let's assume that each of these functions fi is smooth and strictly convex. And I guess actually here, instead of making this a block representation, it looks like based on my notation, I consider these just coordinates of x. Okay, so let's suppose each one of these is just the ith coordinate of x. The dual function is given by minimizing the Lagrangian, right? And we have one equality constraint, so we have one dual variable v. It's unconstrained because it's an equality constraint. So I'm going to add v times b minus a transpose x to the criterion, and I'm going to minimize that over all x. That's the dual function, minimum of the Lagrangian. And okay, this bv is a constant. It comes out, and now here is the really nice part about the dual. You can see that actually I can write, let's say, a transpose x, v times a transpose x, as the sum of v times ai xi. And if I'm thinking about minimizing over xi, I can actually minimize over each xi separately, right? Because I have the following. Something like this. Right? Minimize over all x the sum of fi of xi minus v times ai xi. That's equal to just minimizing each term individually, right? Because each term only depends on one component of x. Okay, and as I said, there's a more general version of this trick that makes the dual very nice that we're going to revisit later in the course. But I'm now just going to define this to be equal to the negative conjugate, that's supposed to be an asterisk, conjugate of fi evaluated at v times ai. Let's just consider that now a definition. Okay, this is a minimum over xi, so it's only going to depend in the end on v and ai. And I'm just going to denote this whole quantity by negative f star or f asterisk sub I of v times ai. And this function is actually something that we call the conjugate of that function fi that we're going to be studying shortly. Okay, but for now, just think of this as a definition. So with that definition, the dual function is succinctly written like this. It's a function, again, of just one variable, and it's b times v, that variable being v, minus the sum of fi star of ai times v. So it's just a univariate function. So that's the dual problem. The dual problem is to maximize the dual criterion, which is, we could maybe pose as equivalently minimizing this. It's not so important, but we can think about it either way. But the point is that this is a convex problem with just one variable. It's univariate, so it's much easier to solve than the primal, right? It's going to be much easier to solve versus this problem. And in fact, in one dimension, I claim that optimization is rather trivial. You can do almost anything you want in one dimension, and you'll be fine. Like grid search is not a bad idea in one dimension, right? Even if the problem was non-convex, grid search would probably be not a terrible idea. There are more clever things to do than grid search, but still, it's a rather kind of easy problem. And as we're going to see later, actually, and as you kind of know already because we've talked about duality, this is not non-convex. This is actually a convex problem. It's convex because it's a dual, and all dual problems are convex optimization problems. It's also convex because we're going to prove that actually the conjugate of any function is itself a convex function. Okay, so this is minimizing a convex function. Okay, but whatever you do, whatever you want to do, you can do grid search, you can do like a binary search, golden ratio, or bisection method, lots of kind of simple things to try in 1D. You'll arrive at some v star, That's the dual solution. And now you know that the primal solution is characterized back by looking at the Lagrangian, right? I know that it has to minimize, it has to solve the problem min over x, sum of fi xi minus ai v star xi, where this was the dual solution. And for the same reason as before, that means that each xi has to minimize this term. Right? I can move the min inside. And now this is a very simple equation that we can use to determine xi. Right? I know that, for example, xi star solves min over xi fi of xi minus v star ai xi. And this is itself quite a simple problem. It's again just univariate, right? Because I'm thinking of xi as univariate here, so I could do something simple. You know, since these were also assumed to be smooth and strictly convex, I could just take the derivative and set it equal to 0. Right? So that's what I'm saying here. You can just take the gradient, set it equal, or in this case, the derivative, since xi is a scalar, and you get a determining equation for xi. So if there was a unique solution to this equation, that would be the primal solution. And there is going to be a unique solution because fi was assumed to be strictly convex. So there's only one primal solution in the first place. All right, any questions about that? It's a bit of an abstract problem since we didn't tell you what the fi's were, but hopefully at least the flow made sense, right? The dual was easier. We solved the dual. We used the stationarity condition to characterize the primal. So here's an outline for the rest of today. We'll talk about dual norms. Then we'll talk about conjugate functions. And I don't need to focus so much on dual cones. That's a bit more of a more advanced topic, but I think it's just good to know that somehow even all the way up to conic problems, there's a very symmetric structure between primals and duals. And last, I'll talk about kind of some dual tricks and subtleties. These are kind of important practical points that I wanted to make, so I'll make sure to spend time on that. And just an editorial comment, there are many other uses of duality and relationships between duality and other interesting topics. I think we could spend a lot of time talking about kind of correspondences between different kind of topics within duality, but there's just not enough time. So if you're curious to know more, you can come chat with me sometime in office hours. So let's talk about dual norms. We've already worked with these a bit on the homework, and we've mentioned these a bit before in class. So let's suppose that this is a norm, and kind of two canonical examples or common examples are something like an LP norm, okay, which is we've used and seen before, but just to be concrete, this is defined as the sum of the pth absolute powers of xi, the whole thing to the power of 1 over p. And this is a norm when p is larger or equal to 1. It's not a norm when p is strictly smaller than 1. So in particular, it's not convex when p is strictly smaller than 1. And the trace norm, which takes a matrix argument rather than a vector, and it returns the sum of the singular values of that matrix, okay, which we note by sigma I of x. The dual norm for any norm, not just for these norms, but just in full generality, is defined by the support function of the unit ball in the primal norm. Okay, so we have some norm. I try to maximize over all z in the unit ball, which means they have norm less than 1. The inner product of z and x, that defines for me what we call the dual norm of x. Okay, and we denote this by norm asterisk. That's our notation for the dual of an original norm like this. And this gives us an inequality that's, you can think about like Holder's inequality, which Holder's inequality is typically taught for LP norms. So I'm calling this like a generalized Holder. But it gives us the following inequality. The absolute value of z transpose x for any z and x is upper bounded by the norm of z and the dual norm of x. Okay, why is that true? It's kind of straightforward to see that from the from just the definition of the dual norm. So let's define y to be z over its, I'm going to say over its norm. Okay, then y transpose x in absolute value is going to be upper bounded by the maximum over all, let's say, w with norm less than or equal to 1 of w transpose x. Right? Why is this? Well, I could have put an absolute value here. This is, it's the same with or without an absolute value because this set is symmetric, right? So if w is in this set, then minus w is in this set as well. And this is just saying that y transpose x is less than or equal to the max of all w transpose x over all w that have norm less than or equal to 1. And of course, by construction, y itself has norm less than or equal to 1. So that's why this holds. But this is exactly equal to, by definition, just the dual norm of x. That's the definition of the dual norm. And if we remember that y was z over its norm, and we just plug in for z and move the norm of z to the other side, we get this Holder's inequality. Okay. So this is often very useful. This type of inequality is often very useful. So some examples, and I don't remember, did we have you, I thought maybe we had you do some of these as exercises on previous homeworks. I can't remember if you'd actually proved that these were the dual norms, but these are at that level. They could be things that you would kind of try in a homework. The dual of an LP norm, so if I look at the dual of the LP norm, it's the LQ norm where 1 over p and where p and q are what we call conjugate pairs or complementary pairs. They satisfy 1 over p plus 1 over q equals 1. Okay, so some important cases to remember are, well, probably the easiest case to remember is when both p and q are 2. So let's call these dual pairs. That's one case. So this tells you that the L2 norm is self-dual. The dual of the L2 norm is the L2 norm. And then this just becomes Cauchy-Schwarz, right? Another easy case to remember is the 1 and infinity norm. Okay, so the dual of the 1 norm is the infinity norm. Okay, and then this type of inequality you could just think about deriving from first principles. Okay, and for matrix norms, the dual of the trace norm is the operator norm. So the operator norm is defined as just the largest singular value. And in fact, I claim this is the analogy of the duality between the L1 and L infinity norms in the vector world. This is the analogy in the matrix world, right? Because the trace norm is like the L1 norm. It's the sum of the singular values. And the operator norm is like the L infinity norm. It's the biggest singular value, sigma 1. Okay? So this is another dual pair. And lastly, the dual of the dual norm. So, you know, this is something that you might ask yourself, what happens if I took the dual of this norm? Well, you can actually show that you get back to the original norm itself. So that means that, you know, for example, that means that the dual of the operator norm is the trace norm. And here I wrote down that the dual of the 1 norm is the infinity norm. Well, that also means the dual of the infinity norm is the 1 norm. Okay, because the dual of the dual gives us back the original norm. So there's a proof I put on the slides. Trying to think whether it makes sense to go through this. Let's skip this for now. I'm worried that I'm going to run out of time to say the stuff I want to say at the end of the lecture, and we'll come back to this if we have time. Okay, it's not, I'd say, a super important proof to go through, which is why we can skip it for now. But the proof is there. It's just, you know, there are various ways to prove that the dual of the dual norm is the primal norm, and this is one of them. So we'll come back to that if we have time. So let's talk about conjugate functions. So this is a very simple concept that, like duality, is very simple. But once you know it, you can see that it actually is very useful, leads to a bunch of interesting and powerful things. We can define for any function f something that we call its conjugate, and I call this f star, but I always use f asterisk rather than star to distinguish between, if I had to like make these really large, to distinguish between the optimal value of a criterion and the conjugate. They're actually not the same. Well, I'm not sure if that's the asterisk, but there is, if you look very carefully, if you zoom in on the PDFs, I'm actually using stars for the optimal value of the criterion and asterisks for the conjugates. But sometimes I'll just call that out loud f star. But to any function f, we can assign another function which we call its conjugate. Sometimes it's called the convex conjugate as well, which is defined as follows. At a point y, okay, the conjugate of f at y is the maximum over all x of y transpose x minus f of x. So it's the biggest gap, okay, that we can observe between a linear function of x with slope y and f of x. And this conjugate f star is always convex, since it's the pointwise maximum of convex functions in y. In fact, it's the same reason why the dual function, the Lagrange dual function, is always concave. It was the exact same rationale. If we take a look at this function, okay, as a function of y, this is a very simple function. It's just affine, right? And now I'm maximizing a bunch of affine functions, okay, pointwise max, over a class of functions indexed by x, and defining a new function as a result. And because each of these were affine, in fact, each of these were convex, the resulting function is going to be convex. It's just the one of our operations that preserves convexity. So that's true regardless of what f was. Right? F could have been non-convex, and you're going to still get out a conjugate that's convex. That's why sometimes we call this the convex conjugate, just to emphasize that it's always convex. Okay, so here's just a picture that I grabbed from Boyd and Vandenberg. If we think about for a particular y, which in 1D y transpose x is just y times x, and y is then a slope we can think about as a slope. We can think about y as kind of like a generalized slope in higher dimensions. This is just the biggest gap between, let's say, the linear function that passes through 0 with slope y and f of x. Okay, which here, this is going to be the conjugate value right here. Right, it's the biggest we can make the difference between x times y and f of x. Okay, for those of you who studied physics or have seen this in other places, when f is differentiable, we often call conjugation, so this action, the Legendre transform. And f star is called the Legendre transform of f. So that's just another word for it when f is itself differentiable. So some properties of conjugates. We're going to see, by the way, to motivate them, that they are very related to duality, and they make dual calculations often a lot easier. So some properties, one property we have is Fenchel's inequality, okay, which says that for any x and y, f of x plus the conjugate of f y is bigger than or equal to x transpose y. Okay, why is that? It's, again, for a very simple reason. If we just take f star of y, that's equal to the max over all, let's call it maybe z, y transpose z minus f of z. And then for any particular x, that's going to be bigger than or equal to y transpose x minus f of x, right, because it's a max. And just rearranged, right, add f of x to the other side, we get Fenchel's inequality. Okay, the conjugate of the conjugate. So if you take a conjugate twice, then if f was a closed and convex function, then the conjugate of its conjugate is itself. Okay, so we don't get any new function out of taking conjugates twice. In general, so let's say if f is non-convex, this is not going to be true, but we'll get that f star star is pointwise less than or equal to f. So for every, let's say, point y, or point x, f star star of x is less than or equal to f of x. Okay, and we get an equality if f is closed and convex. Closed, I think, have I defined closed? I think I've referred to closed a few times. F is called closed. Let's say if all sublevel sets are closed. So if we look at the set of all x for which f of x is less than or equal to t, this must be a closed set for all t. That's one way of defining closedness of a function. Okay, but almost every convex function that you will know is going to be closed. So this just excludes kind of a very small number of functions. Okay. Also under this condition, closed and convex, we have the following super useful relationship between subgradients of functions and subgradients of their conjugates. If you are asking for, let's say, a subgradient of the conjugate at a point y, then a point x is a subgradient of the conjugate at y if and only if y is a subgradient of the function at f at x. Okay, so I switch the roles of x and y between f star and f. Okay, and this statement is itself equivalent to getting an equality in Fenchel's inequality. Okay, having f of x plus f star of y equals x transpose y. So I can't remember, did we have you prove this on the homework that you guys are working on now? Is this on the homework? No? Okay. This proof is in one direction. So in one direction, the proof is fairly simple. And in the other direction, the proof is very hard, unless you remember that f star star is f. If you remember that f star star is f, then the other direction doesn't exist. You just claim that somehow the other direction holds by symmetry. So the whole proof is actually not very complicated once you invoke this property. It's very important to use this property. So let me see how much more we have. I think we still have a bit more. So this might be also something that I push and we can prove if we have some time at the end. But you just basically use the definition of a subgradient and of a conjugate. So you know, we can characterize the maximizing x, okay, by saying it minimizes f of x minus y transpose x. It's equivalent. And then take a subgradient set it equal to 0 to get a characterization for the maximizing x in this conjugate function. And you'll see that one direction of this rule pops out immediately. Okay. Let's actually just push on this rule a tiny bit more before we move on. What happens if f, let's suppose both f and f star are differentiable. So what happens when they're both differentiable? And remember, I'm assuming that f is convex and f star is always convex. So they're smooth and convex. Then the subdifferential only contains one point, right? So this property reduces to the following: x is equal to the gradient of f star at y if and only if y is equal to the gradient of f at x. Right? Again, because the subdifferential just has one point. So what does that mean? This actually means that, let's say the gradient map is invertible. and its inverse is the gradient of the conjugate, and vice versa. This is invertible, and that's its inverse. Okay, so this is a very kind of powerful and important property that this says that this gradient map is actually, in this case, it's invertible, and its inverse is the gradient of the conjugate function. Okay, and the last property is very simple. It just tells us that if we have a function and we decompose it in two blocks, u and v, and we can actually write it as a function of u plus a function of v, then if we take the conjugate, then the conjugates distribute. So the conjugate of my original function, which I can think about as a function of, say, w and z, it's just equal to the conjugate of f1 of w plus the conjugate of f2 of z. Okay, this is very simple to verify right from the definition of the conjugate. So let's go through some examples of conjugate functions, and then we'll tie them to duality. So let's suppose that f is this quadratic, 1/2 x transpose qx, where q is strictly positive definite. Okay, so I have a convex quadratic for my function. So f star of y I can write as max, by definition, over all x of y transpose x minus 1/2 x transpose qx. And this thing is strictly concave, right? You can, if you prefer, you can think about it flipping the signs and saying that that function is strictly convex, but we can also say this thing is strictly concave. So to minimize it, right, I just take a gradient and set it equal to 0. And if I take a gradient and set it equal to 0, I get 0 equals gradient with respect to x, right? We're trying to minimize this over x. I get 0 equals y minus qx, right? So x is equal to q inverse y. And if I plug that back in, I get y transpose q inverse y minus 1/2 y transpose q inverse y, which is just 1/2 y transpose q inverse y. Okay, so the conjugate of a convex quadratic is exactly another convex quadratic where I've replaced q with q inverse. So that's hopefully an easy one to remember. And just I guess an interesting note perhaps is that what does Fenchel's inequality say here? It says that 1/2 for all x and y, 1/2 x transpose qx plus 1/2 y transpose q inverse y is bigger than or equal to x transpose y. Okay, it's a pretty non-trivial inequality, even though somehow everything that defined conjugates and everything we've done so far is very simple. Okay, how about an indicator function? Indicator functions, they have support functions as their conjugates, which is why in previous lectures you may have seen me denote support functions by putting an asterisk at the top of the indicator function notation. So this one is just really rather simple. It's just saying that if we have an indicator function, right, if f of x was just the indicator of x lying in some convex set C, then its conjugate is just the max of y transpose x minus the indicator function of C at x. But right, this thing is either 0 or infinity, so this is nothing more than just the max over all x and C of y transpose x. And that is what we call the support function. This is the support function of C. Okay, what's the conjugate of the support function? of C. There should be no calculation necessary. None in your head. What's the conjugate of the conjugate of a function that's closed and convex? It's the original function, right? And okay, so maybe I should have told you that C is closed and convex. Let's suppose I told you C is closed and convex. Then the conjugate of the support function is the conjugate of the support function. That's what this is. It is the indicator function. Maybe we should use x. Okay, so if you ever had a support function or something like this, and I asked you to take its conjugate, you would have gotten back the indicator function. Okay, and let's also check this one, by the way. What's the conjugate of this quadratic? We should get back the original quadratic, right? Because this function is indeed closed and convex. And we're going to get back another convex quadratic where we have to invert the quadratic form. But that Q inverse is just Q. So we again kind of see that we come back to where we started. And the last one, the last example, I think at least, yeah, is the conjugate of a norm. So if you give me a norm, then its conjugate function, it turns out, is the indicator function of the dual norm ball, of the unit ball in the dual norm. Okay, so if I take the dual norm, call it z star, and I look at the set of all z star, z such that the norm, the dual norm of z is less than or equal to 1, define the indicator function around that. That is the conjugate of my original function, the norm. So how do you see this? I claim actually that's nothing more than an implication of this rule. Why? It's because the norm is itself a support function, right? The norm of x is the dual norm of x, which is the max over all z with dual norm less than or equal to 1 of z transpose x. Right? This is how I would define the dual of the dual norm, but that's just my original norm. So my original norm is itself a support function for the same reasons as the dual norm is a support function. It's just a support function of the dual unit ball. And now I'm asking you, what is the conjugate of this function? Well, I'm just now applying this rule. The conjugate of the support function is the indicator function. And here the set C is this guy. This is my set C. So if I take the conjugate of, max over all z star less than or equal to 1 of z transpose x, the conjugate of this is going to have to be equal to just the indicator function. Okay? So that saves us some proof. We can also do this from first principles, but this is just a shorter way of seeing it, right? Using the kind of circular nature of conjugates. Okay, and maybe the very last time that I'm trying to stump you, but not really stump you. What's the conjugate of the dual norm? Well, we just have to put in the norm here, right? And you can reason that in many ways, that's the right relationship. But it's, again, maybe displaying the symmetry here between conjugates. So let's take a break, and then when we come back, we're going to actually solve it for a dual using conjugates. Let's derive the lasso dual. So we've spent time deriving the SVM dual, which is, I guess, a popular thing in machine learning. You would have seen that in a lot of textbooks and a lot of other courses. The lasso dual is also very interesting, and I think it does tell us a lot about the lasso. But it's less explored in machine learning and statistics. So probably, possibly, I'll say you wouldn't have seen this before, or probably wouldn't have seen this before. And well, one challenge is that if you actually look at the lasso, there are no constraints. Right? Let's look at this version of the lasso, the penalized form, which is a kind of popular form to think about. There are no constraints. So what is the dual function in this case? Right? If I look at the lasso, or really any unconstrained problem, the dual function is a function of beta, and it's also a function of the dual variables, of which there are none, because there are no constraints. So it's just given by the minimum of the Lagrangian over all beta, right? But the Lagrangian is my criterion, because there are no constraints. And that's just f star. So it's very trivial calculation. If you, this is somehow all you tried, you would think that the lasso dual stinks. It's not very interesting. It's just a constant. Right? The dual function is just f star, so we didn't get anywhere. This is true for any unconstrained problem, that the dual is just a constant. And the dual problem is just to maximize a constant. That constant is the primal criterion, so it's not interesting. The primal criterion optimality. But this is where, and I'll mention a bit more at the end of the lecture, a lot of tricks and subtleties come into deriving duals, because we can always reparameterize the primal problem to add constraints in such a way that actually makes the problem equivalently posed. So we're not going to change the problem. We're just going to introduce variables. And then we can derive something non-trivial. We can derive a non-trivial dual. And that's what we're going to do here. So there's kind of an art, in some sense, to doing this, because there are many things to try. But here we're going to actually replace x times beta with z, with the variable z. And we're going to call the primal problem a minimization problem over beta and z of just the norm of, or half times the norm of y minus z squared plus lambda times the L1 norm of beta. And we're going to introduce an equality constraint that z has to be equal to x beta. So of course this is the same as our original problem, right? We've just replaced x beta by z, and then we put an equality constraint. So there's really nothing special we've done so far. But the point is that now we have constraints. So we have dual variables that are not trivially empty. And we can actually derive a non-trivial dual function, a non-trivial dual problem. So the dual function is now to minimize the Lagrangian over beta and z. My primal variables are now beta and z. And the Lagrangian is my criterion plus u transpose times z minus x beta, where u is my dual variable. Right? I write this as z minus x beta equals 0, and this appears in the Lagrangian, u transpose times z minus x beta. Okay, so let's now so g of u is the min over beta and z, we said, of 1/2 y minus z squared plus lambda beta plus u transpose z minus x beta. Let's actually split this problem up into all the terms that involve u and all the terms that involve z, because we can minimize them separately. So first the z terms. The z terms, what terms do I have that involve z? It's just these guys. Right? And what terms do I have that involve beta? It's just these guys. Okay, so both of these minimizations are possible to be done in closed form. One of them is very straightforward. The other is only straightforward because we learned conjugates and learned some rules about conjugates. So this one is the one that's very straightforward. This is just minimizing a quadratic. We have practice with this. We can still do it one more time. So let's take a gradient and set it equal to 0. We get 0 equals z minus y plus u. So we're looking for the minimizing value of z. So we get z is equal to y minus u. And if we plug that in, we get that this whole thing equals let's see, so y minus z is just going to be the norm of u squared plus u transpose y minus u. And okay, for some reason on the slides I decided to write that a little bit differently. Maybe because I wanted to look like a quadratic in u, so just a single term that involved u. So these should be equivalent. Right, so the cross term I'm going to get here is I'm going to get u transpose y. Here I'm going to get a total of minus a half u transpose u, which is what I get why do I get a positive here? No, that's correct. I get a minus a half u transpose u from here as well, and I get the 1/2 y transpose y cancels with this. Yeah, so these are the same. Okay, so I just decided to write it in the slide like this, but they're equivalent. It's just a quadratic in u. Okay, this guy is a little more tricky, right? This guy is not so simple. It's not something that you would know the answer to off the top of your head necessarily, unless you know conjugates, and now that you do, hopefully you can see this kind of pattern occurring. So we're going to write this. First I'll pull out the lambda actually. I'm going to do two things. I'm going to pull out the lambda. I'm going to write this min as a max. So I'm going to put a negative sign in front. I'm going to write max over all beta of what? And that what is going to be u transpose x over lambda times beta. So I'm going to flip the sign and divide by lambda minus the L1 norm of beta. Okay, so I didn't change anything, but I just wanted to write this as the max of some linear function minus some other function, because that's what a conjugate is. That's the form of a conjugate. Right, so this is exactly equal to, if we ignore the minus lambda in front, this max is exactly equal to the conjugate of the L1 norm evaluated at x transpose u over lambda. Right, so maybe I'll just write down here, this is the conjugate of the 1 norm evaluated at x transpose u over lambda. That was the vector whose inner product we were taking with beta in the linear part, right? Which is the argument for the conjugate. So that's going to be equal to the indicator, we know, right, of the unit ball in the dual norm of the 1 norm, which is the infinity norm. So it's the indicator of this set evaluated at x transpose u over lambda. Okay, so let's call this star, and I'll put a star here so you can refer to that later. So this calculation, thankfully, we didn't have to do. If we did it, it would involve subgradients, and we may have could have encountered some errors along the way. But because now we know conjugates, we can just identify this as I said, it's going to be negative lambda times this indicator. And in the slides, I just got rid of lambda because, lambda times the indicator is just the indicator. The indicator is either 0 or infinity, so it doesn't matter what we're multiplying it by. Okay, so this is the dual function, and the dual problem now is to maximize this dual function. But as per kind of a theme that we've seen a lot so far with linear programs and quadratic programs, the dual function actually has kind of like an implicit constraint, right? It has an indicator function in it, so that gives rise to an implicit constraint in the dual problem, right? So this thing we can think about as actually as a constraint in our dual problem, that the L infinity norm of x transpose u over lambda has to be less than or equal to 1. Or in other words, the L infinity norm of x transpose u has to be less than or equal to lambda. If this wasn't true, okay, then this dual function is going to be, it's defined as minus infinity. Right? Since we're trying to maximize it, that's obviously the opposite direction that we want, so we think about it as a constraint. And this is just the criterion. Okay, and because the problem is a problem over u, I can actually drop this term of norm of y squared, and I can flip the sign and consider this a minimization problem. So this is to minimize overall u, the square norm of y minus u subject to x transpose u being less than or equal to infinity. So this is the lasso dual. Okay, we can check that Slater's condition holds because there are no constraints in the primal is convex. So Slater's condition kind of holds trivially in this case, and hence so does strong duality. So we know that somehow the optimal value of the dual and the optimal value of the primal are the same. But note, actually, and this is another point I'll emphasize a bit later, this last dual is actually not equivalent in its optimal value to the primal because I transformed it. Right? I dropped y and I subtracted and I flipped the sign and made it equal into a min. That's just because I like to think about minimization problems, and this problem actually has a particularly simple form. If I actually was running an algorithm and I forgot that I had done that transformation and I calculated the duality gap using this dual, this equivalent dual, I would be in trouble because it's not its optimal value that's going to be equal to the primal's optimal value. It's the optimal value of this problem, right, which is not the same. These have the same solutions. They don't have the same optimal values. So just be aware if you're going to transform a dual to make it kind of more familiar form that strong duality does not probably hold as you intend it to then in terms of the criterion value. It's not like you've ruined the problem. You just have to be careful about what criterion value you're reporting. That's it. Okay, and we can also relate the primal and dual solutions. This is a just from the stationarity condition, actually, exactly. So if we go back to, I don't know why I wrote beta here. This definitely should have been u. But if we go back to the stationarity condition, in fact, we've already done that calculation. I'll just remind you of it here. In order to minimize the Lagrangian over all z, we've seen that we need to make z to be equal to y minus u. So this is the relationship between z at the solution and u at the solution, right here. So I'll put maybe 2 stars here. I'll say recall. Recall that at the solution, we saw that z is going to be equal to y minus u. But at the solution, z is also equal to x beta. So this tells us that the solution to my original lasso problem, x beta, is y minus u. In other words, the dual variable is just the primal residual. U is just the residual from the residuals from the lasso. Okay. How much more do we have? I think I'm going to actually skip this entirely. This was supposed to be a picture that told you why the lasso dual is important. It turns out that you can say a lot about the lasso in terms of its geometry from the dual. I'll just maybe say very quickly, let me say one thing very quickly, maybe you'll find interesting and then we'll move on, is that I can think about the dual problem. It's exactly a projection problem. So this actually is a problem which we say project y onto this set, the set of all u for which x transpose u is less than or equal to lambda. That's all this is. So it's projection actually onto a polyhedron. This thing is nothing more than a polyhedron. And from this, we can actually learn a bunch of things about the lasso. One thing we can learn about the lasso in particular is that is as follows. If I move y around, okay, think about the picture like I have some convex polyhedron like this one, and I have y, and I'm projecting onto the polyhedron. Call this polyhedron maybe C. If I move y around, then the distance between the projections is less than or equal to the distance between, let's say, the y's. If I move y to y prime and I project each of those onto C, then I could not be ending up with projections that are farther apart than y and y prime. That's a property of actually projections onto convex sets. Right? You can convince yourself that's the case. Suppose I move y to y prime right here. I project that guy. This distance is going to be smaller or equal to this distance. That tells me that the dual solution, which is the projection, is actually non-expansive as a function of the data y. Okay, the distance between dual solutions can't be farther than the distance between somehow the initial data vectors that you passed in if you move y to y prime. Because of this relationship, it tells me the same thing is true about the lasso fits. So this actually gives us a rather kind of important property of the lasso immediately, which is that it's non-expansive as a function of the data. If you were to run the lasso on y, run the lasso on y prime, the resulting fitted values don't differ by any more than y and y prime did. It's a perturbation result for the lasso that, again, it's non-trivial, and we just got it for free from the dual. And other things. So I'll just say, for my usual comment, you can come ask about this picture in office hours if you wanted to know more. So why are conjugates so important? This is the reason, is because this calculation we did here was not, what didn't occur by chance. It wasn't like I kind of cherry-picked a problem where conjugates pop up. Conjugates are actually kind of intrinsic to these dual calculations. And they pop up simply because the negative conjugate is defined as the minimum of f of x minus u transpose x, right? I just negated both sides of the definition of the conjugate. And this is exactly what looks like a piece of the Lagrangian, right? If u was a dual variable and f was, let's say, a combination of the criterion and constraint functions or something else, then this is exactly what we see when we minimize Lagrangians, this type of problem. So let me make that maybe more concrete for you. Suppose that we were going to minimize f of x plus g of x. That was our problem. And we wanted to ask, what is the dual of this problem? Well, we're going to have to introduce auxiliary variables like we did in the lasso problem because there are no constraints. So we can write this as minimize f of x plus g of z subject to x equals z. Okay, the dual function is now the criterion plus u transpose z minus x. And we can read off directly, this should say minimize over x and z, by the way, right, because those are our primal variables. Two pieces. So first, the minimum over x, I look at minimizing f of x minus u transpose x. That's just exactly equal to minus f star of u, as I set up here. And the other piece is g of z plus u transpose z. That's exactly equal to minus g star of minus u. So in other words, the dual of this problem is this problem. Dual of minimizing f of x plus g of x is maximizing negative f star of u minus g star of minus u. So anytime you have, let's say, a sum of functions in your criterion, and you can compute their conjugates, you can compute its dual. It's exactly this relationship. So some important examples other than the lasso example, which actually is kind of encompassed by this one. So if I were to look at a constrained primal problem, I can write that as f of x plus indicator function of c at x. And the dual is exactly minus f star of u minus the support function of c at minus u, because that's the conjugate of this function. And for a norm, okay, if I have a f of x plus a norm, then the dual of that problem is to maximize minus f star of u subject to the dual norm of u being less than or equal to 1. Okay, again, that's because the conjugate of this function is the indicator of the dual unit ball. Okay, so these are very kind of handy general rules for duals that should save you a bunch of time once you apply them appropriately. And the lasso was actually just a specific example of this. Right. So one other thing that duals do for you, which is an important thing to point out, is that you can use duality to shift the presence of a linear transformation between functions in your criterion. So suppose you had a problem that looked like minimize f of x plus g of ax, and let's suppose it was really annoying to have that a composed with g, or to have g composed with a. This was a very hard term to deal with. Maybe g was non-smooth and a didn't have a nice structure, or both, and it's hard to optimize this. Okay, if you derive the dual, follow the exact same steps as before. Introduce an auxiliary variable z now that stands for all of ax, add a constraint ax equals z, derive the dual. You'll see that the dual is actually involves f star and g star like before, but a has been shifted from being composed with g to being composed with f, or rather in the dual it's actually f star. So the dual becomes minus f star of a transpose u minus g star of minus u. Okay, and if f was smooth, then this might be a much more favorable problem to deal with. Right, because maybe it's actually easier to work with a composition of a smooth function and a linear transformation. It could be that now you can apply more algorithms to this problem than you could to this one. Okay, so those were just some general relationships between conjugates and duals. I'm going to skip dual cones because they're not important or running out of time. I mean, they're important, let's say, if you were really interested in conic programming, but we're not really doing a lot of conic programming in this class. I wanted just to get to this part, which we now have time for. There's a couple subtleties that you should pay attention to, and I already mentioned them, but I want to reiterate them. So the first is that we often derive a dual problem and then we simplify it. Like maybe we partially solve, or we turn it from a max into a min, or we subtract off constants, or we do all of those things to arrive at a simplified problem that's equivalent to our dual problem. And we just call that the dual from then on. We say that's our dual. Okay, that's all fine because let's say under strong duality, it's somehow the solutions of the dual that you can tie to solutions of the primal. And you haven't changed the solutions by doing these equivalent transformations. But if you're checking the duality gap, you have to be careful because you have changed the optimal criterion value. Right? These equivalent transformations we're describing don't change the solutions, but they can change the criterion value. So that is often the source of a lot of bugs, let's say in programmatic implementations, if you're actually solving the wrong dual with respect to the criterion value. Not with respect to the solutions, but if you're checking the wrong criterion value for the duality gap, then that's not going to give you any guarantees about the primal suboptimality gap. Okay, so this is just a big warning, is that if you're going to transform the dual, remember that when you go to check the duality gap. And the second thing I want to mention is that there's actually a lot of ambiguity into how you introduce auxiliary variables into unconstrained problems. So if we go back to the lasso problem, there were other substitutions we could have made here. Right? I could have actually left this as x beta, and I could have put a z here. I claim that actually will lead to a different dual. It won't be the same dual. It'll actually be, it has to be equivalent to this dual because we have strong duality here, so all duals are equivalent to the primal. But it's going to look different. It's going to actually have like appearances of x transpose x inverse in it. And so for that reason, it's not going to be as appealing, let's say, for optimizing or for studying, so that's why I didn't do that here. But in any one problem, there's going to be typically more than one way to derive a dual if you're introducing auxiliary variables. There's ambiguity there, and so the best advice I can give is try all of them. They're all going to be different dual problems transparently, even though they're all equivalent, and there'll probably be one that has the nicest structure. So there's not just one unique way to derive a dual for unconstrained problems. And the very last thing I'll get to, I think this is the last thing, yeah, is I guess it's similar to what we've been saying so far with the dual norm of the dual norm is the norm, the conjugate of the conjugate is the original function. This is a statement about the dual of the dual, which I think somebody asked about several lectures ago. So we can actually verify that the dual of the dual is the primal in the case, quite easily, in the case that we have linear inequality and equality constraints. So let's suppose this is our problem. Linear inequality and equality constraints. Arbitrary, let's say, convex enclosed function f. If we derive the dual, okay, we can actually directly, let's say, take the Lagrangian of this and now maximize it over u and v, and we'll see that we end up exactly at this problem. And this calculation only involves the fact that f star star is f. That's all we need to do this calculation. It's quite a straightforward calculation. So the dual of the dual we verified is the primal in the case when we have linear inequality and equality constraints. Okay, for general problems, it's actually much harder to verify that this is the case, but it is true and for a very wide class of problems. In fact, it's true as long as, let's say, the criterion and the inequality constraint functions are closed and convex. And again, closed, I think, is really a technicality that you can most often ignore. Most of the functions that you're looking at are going to be closed. In all of these problems, the dual of the dual is the primal. So unfortunately, there's no infinite loop of deriving equivalent problems and getting infinitely many insights from new problems. After you derive the dual, once you derive the dual of the dual, you're back to where you started in most of the problems that you'll start with. Interestingly, I'll just say the proof of this fact that the double dual is the dual in general is really non-trivial. It's not a calculation like this one. And if you're interested in figuring out why, then you can take a look at the Rockefeller textbook, where he defines something called a bifunction, which is a very, very general way to look at dual problems. And in some sense, from this very, very high 30,000-foot view, the problem becomes actually kind of easy at showing that the dual of the dual is the primal. Okay, that was it on duality. I'll see you guys on Monday for the little test. And yeah.